Welcome to Lecture 3.4, Simple Harmonic Motion. In this lecture, we will revisit mass spring systems that we saw previously, and since then, we learned how to solve some basic second-order ODEs, and so we will apply that knowledge to these systems and learn more about them. So, recall that if x of t is the displacement of a mass on a spring, we can think of, if you want to, you can think of the mass, so the mass may or may not be subject to gravity, so it may be something that's moving in this direction. And maybe the external driving force is some engine or something else, but it could also be something that looks like this, where there's an external gravity force, or gravitational force. But either way, if x of t is the displacement of a mass on a spring, then it will satisfy a second-order ODE that looks something like this. Now, this is not exactly the form that we had before. I think previously we put everything over to the left, or everything over to the right-hand side. That doesn't really matter. Let's put it in our standard form and put the x's on the left-hand side. And let's, this 2 is not necessary, but it actually makes things nice because when solving these things, we're going to write down the characteristic equation. Remember that thing involving r, that polynomial, and it's going to turn out to factor nicer if we have a 2 here. And you'll see this shortly. So here, c is the damping constant. Omega naught is the frequency, and f of t over here is the external driving force. So we'll examine all of this in more detail shortly. Okay, so the simplest case, no pun intended, is simple harmonic motion. And so that's a special case of the general equation, and that happens when there's no damping force, that's this, and when there's no driving force, that's this. And in that case, the mass exhibits simple harmonic motion, and x of t, the displacement, satisfies the following ODE right here. X double prime plus kx for some positive constant k equals 0, and so we can express the fact that k is positive by writing it as the square of some number. Here I used omega instead of omega naught. Sorry for the slight inconsistency, though it really shouldn't make a difference. And omega actually does have the physical interpretation as being frequency. Okay, so let me rewrite this equation. X double prime, we've seen this, negative omega squared x. You can solve it using the method of undetermined coefficients that we saw last time, or you can just do it via inspection, which is what I first, this is how I first showed you how to solve this equation in the very first lecture of section 3. So either way, the solution x of t is a cosine of omega t plus b sine of omega t. Okay, so it's a sum of sine and cosine waves, or sum of a sine and cosine wave. But let me ask you, what does this function look like? Like, how would you graph something like this? Obviously, a computer can handle it, but if I were to give you specific values of a and b, like if a is 2 and b is 3, what does that look like? Is it some sort of, is it another sine and cosine wave? Is it some sort of double hump thing? That's not clear. So it turns out that the function like this is always just a single cosine wave or sine wave, but it's shifted a little bit. So there's an alternative way to write this that makes this apparent using polar coordinates, and I'll show you that right now. And it's usually preferable to do this because it's visually clear what this function looks like. Okay, so let's write this down. There's a trick. We can write this as a single cosine wave. And so we do this by switch to polar coordinates. Okay, so let me sketch what this looks like. So here's the XY plane. It's not clear what I'm doing right now. It shouldn't be. So there are two parameters here. That there is this A, and there's this B. So the general solution is as I said before, it's a two-parameter family of functions parameterized by a and b. So let's, how do I want to write that? So let's take this ab, whatever numbers these happen to be, and let's plot them on the xy plane. So let's pretend this point is AB. You may be wondering, why the heck are we doing this? But bear with me for a moment. So this is AB. That's supposed to be a straight line. And let's, instead of expressing this point in Cartesian coordinates, AB, let's express it in polar coordinates. So this line has length or radius, some number. Let's call it A. And that A, by the Pythagorean theorem, is just A squared plus B squared. Okay? Again, A is just the length of that line segment. So now here's a sneaky little trick. Oh, actually, before I do that, I should say one more thing. So let's call this angle phi. So A is greater than or equal to 0, always. And phi, we can assume, is between pi and negative pi. Okay? Okay, so here's a sneaky little trick. X of t equals, well, I'm going to write it first using a cosine of omega t plus b sine of omega t. And now I'm going to switch to polar. So in place of a and in place of b, I'm going to write, well, what am I going to write? So notice this AB is equal, in polar coordinates, is equal to A cosine of phi and A sine of phi. So you can't stop me from rewriting this as A cosine of phi times cosine of omega t plus A sine of phi times sine of omega t. There's nothing wrong with doing that, right? And now we're going to do a trig identity. So this is something that I don't expect anyone to have memorized. I certainly don't have it memorized. But I'm going to write this as A cosine of phi minus omega t. Now, this is using a trig identity. Let me remind you which one this one is. Following a trig identity, cosine of x minus y equals cosine of x times cosine of y plus sine of x sine of y. And notice, this is exactly what we have. We have a cosine of phi, cosine of phi cosine of omega t, plus a sine of t sine of omega t. So doing this thing in reverse gives us this right here. And again, that's not something I don't think any of us, myself included, would ever have looked at and said, oh yeah, do this little trick. But it is a standard trick and it does work. So you're not expected to know that trig identity or be able to derive this, but I want you to get the take-home message, which I will show on the next slide. So this thing here, recall that, let's simplify this. Recall that cosine of negative x is equal to cosine of x. Remember that from a couple lectures ago? So this is equal to a cosine of omega t minus phi, right? And now if I want to, I can factor out, I can write this as a cosine of omega times t minus phi over omega. I don't have to do this, but it makes it a little bit, remember, back when you learned trig and you were graphing trig functions, it made things easier to factor out the coefficient of t to make this monic, because now this is amplitude, this is frequency, and this is the phase shift. So the big idea here is that any function of this form, a cosine omega t plus b sine of omega t, in other words, the solution to this differential equation for simple harmonic motion, can be alternatively written as a single cosine wave of the following form: a cosine of omega t minus phi, or if you want to, you can factor out the omega and get something like this, because now you know from basic trig that this is your amplitude, this is your frequency, and this is your phase shift. And so amplitude A is the square root of a squared plus b squared. Recall that. So you can actually get it explicitly from this A and B. And the phase shift, of course, is phi over omega. And omega is, I want to say, in quotes, the inverse tangent or arctangent of b over a. And I say in quotes typically when I'm lying, because that's technically not perfect. And so why is that not perfect? Well, let's draw let's draw a few pictures. Let's say that A and B happen to lie in the first quadrant. So let's suppose that this point here is A over B. Then if you plug into if you take your calculator or computer and you type in inverse tangent of b over a, it will give you the right answer. It will give you this angle phi. And recall that, just to remind you where this formula came from, just by basic trigonometry, this length a, this is a, and this is, by the Pythagorean theorem, the square root of a squared plus b squared. Okay, so this is the case for when we are in the first quadrant. This is indeed a correct statement. However, if we are in the second quadrant, like let's say that we are in the second quadrant. In other words, our point AB happens to be over here. Well, that means that the angle that we are looking for is actually in this range. It's bigger than 90 degrees. So if you pull out your calculator and you type in the inverse tangent of b over a, it's going to give you an angle between negative pi and positive in this range, and positive, not negative pi over 2 and positive pi over 2. And the reason is because this angle over here, let's try this again, this point over here, negative a and negative b, the reflection of or the rotation of this by 180 is going to have the same tangent, because negative b over negative a is positive b over positive a. So in that case, what you get is the answer your calculator gets, you have to add pi to it to get the answer that you want. And similarly, if we are in if we are in the third quadrant, and we have an A and a B over here, and this is our phi, then your calculator will and you type in inverse tangent of b over a in your calculator, it's going to give you a negative a and negative b, or it's going to give you an angle actually. It's going to give you this angle because the tangent of negative b over negative a is the same as the tangent of b over a. So in that case, you also have to add pi to what your calculator or computer gives you. So to summarize this, let's actually write this down. Let's say note. Since phi is between negative pi over 2 and positive pi over 2, and I should say for calculators, the actual value of phi, so I'm fixing this little statement, this thing I have in quotes, the actual value of phi is inverse tangent of b over a when we are in quadrant 1 or quadrant 4. I didn't actually write down quadrant 4, but it's the same case as quadrant 1. Your calculator gives you what you want, but it's the inverse tangent of b over a plus pi if we're in quadrant 2 or 3. Okay, so let's do an example to this. Let's just suppose that let's suppose we have negative 3 cosine of t plus 4 sine of t. So this is an example, and let's write this as a single cosine wave. So that is so in that case, this is equal to, it's equal to something like, I don't want to say it, so it's equal to something like this, where a, I'm just thinking how to organize this. In that case, a is the square root of 3 squared plus 4 squared, so that is 5. Technically, the square root of negative 3 squared plus 4 squared, it's still 5. And the inverse, sorry, not the inverse, the angle phi is the arctangent of b over a, so that is so that's 4/3. Now, this point, negative 3, 4, lies in quadrant 2, so we should type into our calculator this, inverse tangent of 4/3 plus pi. And your calculator is going to give you, I've actually did this one in advance, so inverse tangent of 4/3 is negative 0.927 plus pi. I'm actually not going to simplify this. I think it's easier to leave it like this, because if I were to combine this into one number, it's not clear where I got that from. Okay, so now we can say that this function that I gave you is equal to 5 cosine, and I made it easy. I didn't change the frequency. The frequency is just 1. So cosine of t, that should be a pencil, t minus, and then let me just add this number in here, whatever the heck that is. That's my phase shift. Well, phi divided by omega is 1. Again, it just makes things easier. So negative 0.927 plus pi. Okay. So let's do an example of a simple harmonic motion ODE, a word problem, and we'll put together what we've learned earlier in this chapter and also earlier in this lecture and earlier in this chapter, both about solving and simplifying our solutions. So here we have a 2 kilogram mass is suspended from a spring. The displacement of the spring once the mass is attached is 0.5 meters. So let's draw a picture of this. So we have a spring here. We put the mass on. The spring not expands. What should I say? Should I say this? I should say it displaces by 0.5 meters. So this is this distance right here is 0.5 meters. And then from here, so the equilibrium position is right here. From here, the mass is displaced 0.12 meters downward from this equilibrium. So we pull this even further down. So in other words, we take this mass spring system and we pull it down a little bit more. So now this is 0.62 meters. This is 0.5 meters. And then we let go. What's going to happen? This spring is going to bounce back and forth forever, assuming that there is no damping. So let's set up and solve the initial value problem that models this. So the first thing to do, well, is to determine the spring constant. So let me write this down. Determine the spring constant. So at equilibrium, when the mass is hanging here, motionless, that means that the gravitational force. So we have a force going down. That's gravity. This is mg. We have a force going up. That's the spring force, which is k times the displacement, and those things cancel themselves out. They're equal. So in other words, to determine the spring constant, we set k x naught equal to mg. Remember, k is that spring constant from before. So m is something we know. It's 2 kilograms. G is a constant. Say it's like 9.8. And then x naught is the displacement. That's 0.5. So k equals mg over x naught. And for this problem, I'm going to suppose g is actually 9.8. So this is 2 times 9.8 over 0.5, and that is 9.8 times 2 is 19.6 times divided by 0.5 is times 2 is 39.2. The units that we need are Newton meters. This is something that's really important in your physics and engineering class. I'm not too worried about if you know what a Newton meter is. Okay, so so now that we've determined what this spring constant is, let's set up the differential equation. So how do I want to write that? So second, let's use Newton's second law. So that is force is mass times acceleration mx double prime, which is the sum of the forces that act on the spring. And in this case, it's just going to be gravity, and it's going to be the spring force. So how do I want to write this down? So m x double prime. That's the total force acting on the weight. Let me write that down. Total force. That equals, in general, negative mu x prime. This is the damping minus the spring force, and then the gravitational force. This is from the very first lecture in this section. So this is just for completeness. I'm putting this all in. Oh, I meant to make that black. So this is damping. And it's 0, so this is equal to 0. This, of course, is the spring. This, of course, is gravitational. So in this case, we don't have damping. So we can simplify our ODE. We can write this as mx double prime equals negative kx plus mg. I guess I didn't need to write that again because I have it up here. Although anyways, I can write this as 2x double prime equals negative. Now, if I want to, I can just plug in numbers. Instead, I'm going to do that one step later. Kx. Now, instead of mg, that's equal to kx naught. So I'm going to write this as plus kx naught. And really the only reason I'm doing that is so I can just factor out the k first. Makes things slightly easier. So I'm going to write this as, that's equals negative k times x minus x naught. Recall x naught is our initial displacement, which is 0.5. So this is, let's see, this is equal to negative 39.2 times x minus x naught, which is x minus 0.5. So to summarize, we have a differential equation, 2x double prime plus 39.2 times x minus 0.5 equals 0. That's our equation. And I should also say, I said initial value problem, so I should tell you what the initial values are. Now the first one you can see right away, it's the mass is displaced 0.12 meters downward from equilibrium, so that's 0.62, starting from counting right here. So we have x of 0 is 0.62. And then we actually need one more. Recall that we have a second order equation, and we want to solve it. We need two initial values. So the second one is less obvious, but it's the mass is displaced 0.12 meters downward, so we pull it down and then we let go. In other words, we don't push it up, we don't pull it down more, we pull it down, hold it, and let go, which means that initially the velocity is 0. Think of it as like taking a ball and dropping it from a roof. Remember those problems where you drop balls from roofs and you measure the display or the height from the ground. So you're pulling this and letting it go. That means the initial velocity is 0. So x prime of 0 equals 0. So here is our, so I guess we have done the first part. We have set up an initial value problem that models this, and next we need to solve it. But that should be the easy part. I think you probably agree that everything we've done so far is harder than what we than solving this, which is things that we've spent the last few lectures on. Okay, so on the previous slide, we set up the initial value problem for this system, and now we're going to solve it. So let's actually write down what that problem is again. It was 2x double prime plus 39.2 times x minus 0.5 equals 0, and then x of 0 equals 0.62, and x prime of 0 equals 0. So I'm going to rewrite this one more time in our standard form. 2x double prime plus 39.2 equals 19.6. Actually not quite our standard form because I didn't divide by 2. It doesn't matter. The homogeneous solution is going to be a cosine of omega t plus b sine of omega t. Right, here I'm using a and b instead of c1 and c2. And omega, of course, is... Oh, I skipped something. What did I do wrong? And there needs to be an x there, obviously. So omega is the square root of the coefficient of x. So if I divide through by 2, I get 19.6, and that's omega squared. So notice that omega squared is 19.6, so omega is the square root of 19.6. So I'm going to actually, instead of writing the square root of 19.6 everywhere, I'm going to leave it as omega and just tell you what omega is throughout. I think that's easy. Okay, let me actually draw the situation that we have again. So we have a spring that goes down to here. When we put a mass on, it stretches down 0.5 meters, and then initially we pull it down even further. So it's 0.62 meters. So this is okay. So this is the homogeneous solution, obviously. And how about a particular solution? So what is a solution that solves this? Well, is there a constant solution? Okay, how would you do that? Well, if there's a constant solution, so I'll show you two ways. I guess you already know one way, but if there's a constant solution, that means that the derivative is equal to 0. So that means that this term is 0, and solve for x. And you can see right away that x equals 0.5. So I'll write that down. Particular solution is 0.5. But let me ask you if there's another way to do that. So this mass spring system, you put the mass on, and it hangs down to here. And let's suppose that you don't exert this initial little downward displacement. In other words, let's suppose that instead of these initial conditions, let's suppose that you had, do that over the side, x of 0 equals 0.5. Come on, 0.5. I don't know why this pen is having trouble now. And x prime of 0 is 0. In other words, suppose you just left the mass hanging right here at 0.5 meters. It's not going to move. It's going to stay still forever. In that case, you have a constant solution. The displacement of the mass is fixed at 0.5 right here. So it's always nice when you see something you know mathematically to be true match something that you know intuitively to be true. Okay, so we're done. Well, almost. So the general solution is y of t equals a cosine of omega t plus b sine of omega t plus 0.5, where omega is assumed to be this root 19.6. So let's use our initial conditions. This one is typically simpler because we don't have to take a derivative first. So it probably shouldn't matter which one we do first. So let's use, come on, pen. Let's use the initial conditions. So the first one, oh, I said y of t. I'm so used to that. I should say x. Should be x of t. That look like an x to you? Well, what if I made that red? X of t. Okay, there. So use initial conditions. X of 0. So plug in 0. When we plug in 0, we get be careful. We get a times cosine of 0 is 1 plus 0 plus 0.5 and set that equal to 0.62. 0.62. I'm going to take the time now to cross this out because I don't want that to be a distraction. Those were not our original initial conditions. So that means that A is, obviously that means A is 0.12. A is 0.62 minus 0.5. And let's use our second initial condition. So we have to, for this one, we actually have to take the derivative of the function first and then plug in 0. So x prime of t is negative a omega sine of omega t. I could have put in 0.12 if I wanted to, but it's not going to matter. I don't think anyways. And then plus b omega cosine of omega t. So let's plug in 0 into this. X prime of 0 equals negative a omega times 0, actually, so it really doesn't matter. 0 plus b times omega times 1, and that equals 0. So that whole thing is 0. Omega is not 0, it's root negative 19.6, and so that means that b better be equal to 0. B equals 0. So our final solution is, let's squeeze it in here, x of t is 0.12 cosine of root 19.6 t plus, it's supposed to be a t and that's a plus, 0.5. And actually I lied, I'm not going to be using our phase shift in this example, but I will do one shortly in examples in the next lecture. So before we finish, let me point something out here. Let's make sure this makes sense. So what is this saying? This is saying that the solution, the displacement, is a cosine wave with amplitude 0.12 and starting at 0.5. And think about if that makes sense. The mass goes down here. So from here, this is our equilibrium. So from this point, when we pull the mass down, what's going to happen? We pull the mass down 0.12 meters. It's going to bounce back and forth like this. This is going to be a cosine wave with amplitude 0.12. It's going to go 0.12 below and 0.12 above. And that is exactly what we have here. A sinusoidal, or I guess there's no cosinusoidal word in the English language, I don't think anyways, but it's a sinusoidal or a harmonic, it's simple harmonic motion. It's going to oscillate back and forth with the amplitude 0.12 and displacement 0.5.